So two days to do most of the sections in this chapter. So that's pretty good. It takes a little while for the ideas to kind of sink in and make sense. Okay. All right. So, fellas, if we could. So this section was on something called the definite integral, and we started off by finding the area of this shape that we hadn't seen before because we were used to dealing with things that had all the curve above the x-axis. The function was always positive, therefore the heights were always positive. So we introduced the idea going through the exact same process. We did four little rectangles on this on this interval from 0 to 4, and we introduced this area, the concept of signed area. If we're adding up the area from left to right, areas above the x-axis count as positive, areas below the x-axis count as negative. Again, going from left to right, so moving in a positive direction and accumulating areas. Anything above counts as positive, anything below counts as negative. Okay? So we have positive signed areas, negative signed areas, and then we talked about the net area is what we get when we add all those together. In the end, how much have we got? So we had an estimate of -5. We recognized that there was some positive area up here, but a whole bunch of negative signed area here. So the net area kind of made sense that it was negative. We introduced what we call the integral sign, and the definite integral means we're integrating from this lower limit to this upper limit. And then we went through several key points about this and some properties of this. We talked about how we're used to dealing with this limit as n approaches infinity, the sum from 1 to n. So this sums up all of these rectangular areas, these heights times these widths. And we talked about why the notation kind of makes sense, why they use this lazy looking s, why we have this lower limit of a and the upper limit of b, and how that's still the function height and the dx is the width. We went through a couple properties here, talked about those, and we talked about how using Theorem 4, this is the idea that we've been using. Partition it into a regular subinterval, nice equal subintervals. Use right endpoints because they're relatively easy to evaluate. And then we went through, for this actual problem right here that we estimated at the beginning, we went through and we found the exact net area. The exact net area was -16 So we also made the point that this thing right here, this definite integral, is a number. It's a number that represents the signed area. So when we go through and find that, we ended up with -16 for an answer. That is the answer to that definite integral. Okay? Then when we flipped the page over, we were looking at some of these, and all we had to do on a few of these was just set up an expression, set up a definite integral that would find the area. So this definite integral from 2 to 5, again, we used Theorem 4, we used that technique, regular subintervals. This was 3 units long, n equals subintervals. This would represent the right endpoint where we'd evaluate. So we take that right endpoint, plug it into the function. Again, these right here are the heights. This right here is the width. And we pointed out that now you can look at it and you can tell, oh, the function is e to the x. We're starting at 2 and we're going 3 units. So it must be the integral of e to the x starting at 2 and adding up all the area from 2 to 5. So we pointed that out on this one right here. Again, it was a square root function, but you can see the square root. You can see how wide the interval was. It was 8 units wide, and we started at 1. So if we started at 1 and went 8 units, it would be the definite integral from 1 to 9 on that square root function. So really all we're doing is we're adding up all of this area from 1 to 9. That's what the definite integral would be. And here clearly it would be positive because all of those function values are positive. Okay? And then in this next part we talked about finding these answers, even though they might be a little bit more complicated of a shape, and doing it using geometric areas. So this was the top half of a circle, happened to be a circle centered at the origin, radius of 2. So we find the formula for the area of a circle, and then we just take half of it. That is the exact answer. At some point, you'll get to the point where we could actually find this using what we call an integration technique in antiderivatives, which is what we're learning in this chapter. We're just kind of building up to that. We took this one right here, and we interpreted this as an area that was below the x-axis, so we counted this as negative, we counted that as positive. So we had -1 for the area below, +9 for the area above. So the net area of the whole thing was +9. Sorry, +8 in this case. And then we looked at an example. This is the definite integral, all of the signed or all of the net area from -pi to pi on the sine function. Well, the sine function is an odd function, and it looks like this. So whatever area this was, it would be negative. Whatever area this was, it would be positive. And we know something about those. We know about the symmetry. We know those areas would have to be equal. One's negative, one's positive. So by the time we're done adding these up, we'd end up with 0. All this negative would be canceled out by all that positive. Any questions there? Okay, so now we're going to have a little bit more fun. We're going to look at some of these, and we're going to actually figure out some of these geometrically, and then we're going to start to develop some formulas that might look a little bit familiar and are going to lead into section 5.3, which we'll cover Wednesday and Thursday, which is on the fundamental theorem of calculus. The most important theorem in all of calculus. Oh, it'll be fun, believe me. Okay? So we're going to interpret these as areas. So we're going to look at these as geometric shapes. So I'm going to draw this right here. So this is just a constant function. Constant function here. We're going to accumulate the area from 1 to 5. So that would be from here. I'll just kind of put a wall up right there, all the way to 5. Put a wall up right there. Very easy to tell. We don't even have to slice this up because it is one big rectangular shape, one big rectangle. It happens to be 4 units wide and 2 units tall. So the net area on this one is 8. So there's our answer. Okay? This is the definite integral, or the signed area that accumulates from 1 to 5 on the function x, the identity function. So I'm going to draw the identity function. So that's a perfect 45, just kind of slope of 1, looks something like this. And we're going to go from 1 to 5. So we're going to start right here. I'll kind of put a little wall up right there at 1. And here's 2 and 3 and 4 and 5. So this is the area that we're after right here. Okay? Any ideas? It is a trapezoid. Okay? So let's find this using the area of a trapezoid. The area of a trapezoid is 1/2 B1 plus B2 times h. Trapezoids, the height is the distance between the two parallel sides. So the height on this one is actually the width that we're talking about here. So we need to know how far it is from here to here. That, of course, would be 4. And I need to know how tall this one is. This is 1 unit right here. And this is, remember, we're stopping at 5, and this is the identity function, so this is 5. So that means our area is going to be 1/2 of B1 is 1, B2 is 5, and the height is 4. So I'm going to cancel this with this. That's going to be a 2, not a square, but just a 2. Okay, so that's going to be 6 times 2, so our area is going to be 12. Any questions? Okay, we'll do the same thing with this next one. You'll notice that I'm keeping all of these from 1 to 5. So let's draw this one. This one crosses at 2 and has a slope of 1. So here we are at 1, 2, and a slope of 1. So it looks something like this. And we want to accumulate the area starting at 1. So I'll put the little wall up here, and then 2, 3, 4, 5. Put a little wall up right there, and we want that area. So again, we're going to do this using a trapezoid. So it's 1/2. If I plug a 1 in, how tall is the first base? 3. Okay, so that's 3. And if I plug a 5 in, how tall is that base? 7, right? Okay, so this is going to be 3 plus 7. And then how far is it from here to here? It's 4. So I'll cancel this with that. That's now a 2. So I get, it's 20, right? Any questions? Really cool when they're nice geometric shapes like that. Okay, good? Okay, so you've got some problems that are very similar to that. And let's read through this right here, and then we're going to talk about some properties of integrals, and we're going to point out some interesting things here. So it says, when we approximated that function at the beginning of class yesterday, and then when we figured out what it actually was, okay, we had some function values that were positive. We had parts of the graph that were above the x-axis and parts of the graph that were below the x-axis, okay? And the way we accounted for that is we said the negative heights, okay? We said, well, since area can't be negative, we called the product of the positive width, because we were going from left to right, we were going in a positive direction, so we had positive widths, and a negative height, we just called that the signed area. So even though the product was negative, we kind of just said, well, the negative means it's below the x-axis, but the number actually means the area of that particular rectangle, okay? So we called that the signed area. But think about this. The widths were positive because we were going from 0 to 4. We were moving in the positive direction. We were going from left to right. Well, what would happen if we just changed the direction and we said, you know what? Instead of adding up these rectangular areas going from left to right, going in a positive direction, what would happen if we switched and we went from right to left? We went in a negative direction. What would the widths be then? Each one of those delta x's, because we're going to move to the left, we're going to move in a negative direction, each one of those delta x's would be negative. So we'd have negative widths in every case, okay? So if you've got negative widths, because you're going from right to left, if you're moving in a negative direction, what would that make the product of a negative width and a height that's below, a function value that's below the x-axis? Positive. It would make it positive, wouldn't it? And anything above, you'd have a negative width and a positive height, so anything above would count as negative, okay? So that little thought process there brings us to these properties of integrals, and these are all very useful, so they're pretty important. So let's take a look at this. The first one is what we call a zero-width interval, and we love these. If you're integrating from a to a, it doesn't matter how ugly the function is. If you start adding up at 7 and you stop at 7, you're not going anywhere. You're not accumulating any area underneath the curve, so the answer there would be 0. So even if I have something that's really ugly looking, which I'm not sure I could even get the answer to without a calculator or a computer, it is a little bit comforting to know we're integrating or we're accumulating area from 1 to 1. We don't go anywhere, so the answer is 0. If we take a look at this one right here, this says a constant, if we're integrating from a to b, is just the constant times the difference between b and a. In other words, this is how tall it is, that's the height, and this is the width of the entire interval. So as an example of that, we just did one like this. We did this one right here. It's constant. So we could get this same answer. We looked at it and we were drawing pictures and all of that sort of stuff. We can do the same thing here and get the right answer. Because if you'll think about it, we did this exact same thing in our heads looking at the picture. So this says, take the constant, which in this case is 2, and multiply it by b, which is 5, minus a, which is 1. Isn't that 2 times 4? And isn't that 8? Okay? And it works every single time, because all you're doing is, because you have a constant height, all you need to figure out is how wide is our rectangle, how wide is our interval, and then how tall is the function. Okay? If we have something like this, so look at the difference. If I'm integrating from b to a on the same function, as if I integrated from a to b, this is going from left to right. This is going in the opposite direction. So guess what happens? You can just put a negative in front of it. So if I take that same exact one and I'm integrating from 5 to 1 instead of from 1 to 5, the answer is going to be the exact opposite. The answer is going to be negative 8. Because anything above the x-axis, because we're integrating in a negative direction, I've got a negative width and a positive height. It's above the x-axis, but I'm integrating in a negative direction. I'm integrating to the left. So it's going to count as negative. The cool part about this is, see this formula up above here? It works also. So this would be the constant. What's B? 1 minus A, 5. This is going to be 2 times negative 4, which is negative 8. Same answer either way. Pretty cool how all of this works together. Any questions there? Okay, let's take a look at the next one. This is kind of like the sum and difference rule that we've learned with limits and integrals and stuff like, or derivatives and stuff like that. If I have the definite integral from a to b of two functions that are either being added or subtracted, I can find the definite integral of the first one, the definite integral of the second one, and then perform the operation, whether it's addition or subtraction, and then get the answer. So we've got one like this up above. We had the integral from 1 to 5 of x plus 2. So I can find the definite integral from 1 to 5 of x, the definite integral from 1 to 5 of 2, and then I can add the two of those answers together. So this answer, let's look up above and see what it was. That was 12. This answer was 8, so I end up with a whole answer of 20. Now, here's what we really did. Okay? If you think about this geometrically, if we keep the two of these together, I've got a picture of it right here. What really happened was, I've got this function 2. The area from 1 to 5 on the function 2 can be represented right here. It's this rectangle right here. If I then stack this trapezoid on top of that, I'm literally adding the two areas together. So I took these two pieces, put them together. It works whether I do it all together and find it geometrically like this, or if I find the two separate pieces and then add them together. Again, geometrically, they'd just be stacked on top of each other. Any questions there? Okay. So let's take a look at this one right here. This says the integral from a to b of a constant times a function. We can slide that constant out front and we can find the definite integral here, and then we can times it by the constant. So if I have this problem right here, the integral from 1 to 5 of 3x dx, I could take the 3, slide it out front, leave the function right there, and then I can figure out the answer. The answer is going to be 3 times whatever this was. What was this one again? Wasn't it 12? So the answer on this problem is 36. Now, this is important. I'm going to scribble over this right here just so I have room. Here's what happened here. Here's the function y equals x. Here's what we did before. We found the area between 1 and 5. So we did this. We added those up. And that area happened to be 12 on that trapezoid. If I were to take this and I were to put a 3 in front of that line, that vertically stretches it. It makes it 3 times taller than it used to be. So this rectangle right here is now this tall rather than how tall it was before. This rectangle right here is now this tall rather than how tall it was before. Forgive my scale right here, but it's reasonably close. If every one of these rectangles is 3 times taller than it was before, what's going to happen to the area? It's going to be 3 times bigger than it was before. So that's kind of the rationale for the constant multiple property here. Any questions? Okay, so let's take a look at this last one, and this is kind of interesting. This is the integral from a to c, f of x dx, plus the integral from c to b, f of x dx. That should equal the integral from a to b. So here's what happens. Okay, rather than going from a to c, stopping and getting an answer, then starting up at c and going to b and getting an answer, and then adding the two together, why bother stopping at c? Why not just integrate from a to b? Does that make sense? So the integral from negative 2 to 0 on that function, plus the integral from 0 to 2 on that function, should just be the integral from, start at negative 2, stop at positive 2. So let me show you what this looks like. Does that look familiar? Okay, I need to slide it up. You can just look at the top of the page there. Okay, here's the idea on that one. The first one was the integral from negative 2 to 0. That would be adding up all of this signed area right there. The second part was adding up this signed area from 0 to 2. Well, why bother stopping at 0 if you could just integrate from -2 all the way to 2 in one fell swoop? Okay? Does that make sense? Okay. Go ahead and flip the page over, and now we're going to look at a nice application of this, something that's actually kind of interesting and extremely useful. So if you look at this last little property right here, it's an equation. And just like any other equation, it can be algebraically manipulated. So as long as you do the same thing to both sides, you could multiply both sides, you could add, you could subtract, whatever it is, and you could move things around to get another true equation as long as you don't break those rules of algebra. Okay? So again, this is the idea behind this one. If we integrate from a to c on this particular function, we're going to get this signed area right there. If we then integrate from c to b, we're going to get this signed area right there. So the integral from a to c on that function plus the integral from c to b on that function is exactly the same as if we just started right here and we just added from here all the way to there and we never stopped. Okay? So what if I said, well, I just want from c to b. All I want is this right here. Okay. So the idea is we're going to take the whole thing, because I don't want the whole thing. I only want from c to b. But let's say I knew what some of these quantities were and I could solve for the piece that I don't have. What I do is I take the whole thing and then I just subtract off the piece that I don't want. So if all I want is from c to b, I'm going to take the whole thing. So I'm going to take the integral from a to b, f of x dx, and I'm going to subtract off the piece that I don't want. What piece don't I want? I don't want the stuff from a to c. So notice all that I've done is I've taken this equation right here and I've moved the integral from a to c over on the other side. So I've got the whole thing subtracting off this piece that I don't want, and that just leaves the integral from b to c. Now that seems weird. It's like, well, why wouldn't you just find that directly? Because sometimes you're not given how to find it directly, but you're given other information that will help you find that. So what if I only wanted from a to c? I'd take the whole thing from a to b, f of x dx, and then I would subtract off the piece I don't want. If what I want is from a to c, I'd subtract off from c to b, f of x dx. Okay. Make sense? We'll see how much sense it makes in just a second. Let me just reiterate, just while we're at it, please don't lose sight of the fact of what a definite integral represents. Okay? It's all right there for you. You need to be able to look at these integral signs and be able to tell what it's asking for. This right here is asking for the net area that accumulates underneath this curve between A and C. This right here is a height, and that right there is a width. So we're literally taking that limit as we slice this area up into a bunch of little rectangles, add up their areas, and then take the limit as this number of slices approaches infinity. So each one of them is infinitely small in width, and yet when we add them up, they'll have a limit, and it will be that signed area between the curve and the horizontal axis. Okay? All right. So let's use some of these properties here. So this is a good test type of question because it gives you information, and without an understanding of these properties of integrals, you really don't have much hope of getting these answers without understanding the process here. So this looks like a really ugly notation here. If we showed this to you even earlier in this, maybe even 1 month ago, this would be like, I have no idea what to do with this. But now what's the answer? Answer's 0. Okay? Because it's a 0 width interval. This is asking us to add up area, but it doesn't give us an interval on which to add. We start at 2 and stop at 2. We're not going anywhere, so we don't add up any area. We've got 3 times f of x. That's going to be our height. Here's our width, and we're going to add up from 1 to 2. Well, let's take the 3 and slide it out front and see if we've got something that they did give us an answer for. So we've got from 1 to 2 f of x, we know that's -4. 1 to 5 f of x, that's 6. And 1 to 5 g of x, that's 8. Well, this is a quantity that I know. This quantity right here is this quantity right here. So my answer on this one is 3 times -4, so the answer is -12. Let's take a look at this one right here. We can use the difference property here. This would be the integral from 1 to 5 f of x dx minus the integral from 1 to 5 g of x dx. Now, a lot of students they'll leave off the dx on both of these. They'll just say, gosh, it's an integral. Let's just know what function it is. Why would it be a bad idea, in theory, to leave off the dx? Yeah, I mean, it has a literal interpretation. It's the width. It's the difference in x. Okay, so do I have this value right here? I've got a 6. Do I have this value right here? I've got an 8. So the answer on this one is 14. Oh, it's a minus. Thank you very much. Okay, -2. How's that sound? Much better because it's correct, right? Okay. Any questions there? How about the next one? Okay. All they did is it's still 5 and 1. It's still the function g, so it's still this guy right here. But now they changed the order of integration. Instead of going from 1 to 5, we go from 5 to 1. So the answer is the opposite of what the signed area would have been before. There were 8 units of signed area in total above the x-axis here. Okay, so we count those as below because we're going in the other direction. How about this one? Okay, they don't have any that are from 2 to 5. I've got from 1 to 2 and from 1 to 5 on f. So if I only want from 2 to 5, I'm going to take the whole thing. I'm going to take the integral from 1 to 5 f of x dx, and I'm going to subtract off the piece I don't want. What piece don't I want? I don't want from 1 to 2 f of x dx. So that's going to give me 6 minus -4. So that's going to give me 10. So the answer on this is 10. Now, just for the heck of it, let me show you how we could kind of interpret this geometrically. So here's G. Oh, I'm sorry, this is F. Okay. We know that the integral from 1 to 2 is -4. So let's say I start at 1 and I go to 2. Okay, and I end up with a -4 there. Okay. Here's what I know. I know that by the time I'm done and I get to 5, so start at 1 and go to 5, I know that I end up with 6. So if I started at -4 when I went from 1 to 2, so if this area was -4, and by the time I'm done adding up all the area between 1 and 5, I end up with 6, what would that right there have to be? If I started at -4, and by the time I got done, I ended up with 6, what must this piece be? 10. It's got to be 10. Okay. Now, that's a simplified example. I'm not saying that's exactly what it looks like. Okay. It could certainly go above and below the x-axis on both parts, but that's a simplified view of how you can reason your way to the answer. Okay. Any questions? Sure? Okay. Then go ahead and take this part and break it up. This part shouldn't be too bad. It's going to look like this. Four times 6 minus 8. Answer is 16. Okay, are there any questions? Okay, nice little properties. They're pretty cool to work with. I've then got this diagram. So a lot of this is just being acquainted with the notation, what we're talking about when we talk about net area and all of that sort of stuff, direction of integration, how we can use these properties to find answers. So I've got a picture right here of a function. Okay, looks like a pretty nasty looking function. And what are indicated right here are just areas. These are areas. Now, they colored this one slightly differently because it's below the axis. And over here, we're going to be asked questions. The reason they didn't make these positive and put a positive 16 and put a negative 5 here is because it depends on what the direction of integration is. If I were integrating from A to B, the answer would be negative 5. But if I integrated from B to A, the answer would be positive 5. Okay? Direction of integration makes a huge difference. Now, when we put all these together, all we need to do is be careful. So watch me, because I've got to be careful also. When I go through and do these problems, I just need to look very carefully. Where am I starting adding up net area, and where am I stopping? So I'm going to integrate from 0 to A. So that's going to be from right here to right here. I'm integrating in a positive direction. This entire portion is above the x-axis, so the answer here is 16. For B, I'm going to go from 0 to B. So I'm going to start right here, and I'm going to end when I get to B. So all of this counts as positive. All of this counts as negative. So what is the net area here? 11. Okay? So I'm trying to do this slowly enough that you can look at it and think of what the answer would be in your head, and if you get it right, then we're in good shape. So we're going to go from 0 to C. Start here, go all the way to there. We're integrating in a positive direction. Anything above counts as positive, anything below counts as negative. So if I add up the two positive areas, I get 27. If I subtract off the negative area, I end up with 22. Or if you just take the last answer and continue integrating, add another 11 to this, that would get you 22 also. Now I'm going to go from A to B. From A to B, integrating in the positive direction. This whole area is below the x-axis, so this is going to be negative 5. 0 to C. Did I say that right? Always start at the bottom. This is the lower limit and this is the upper limit. So that means we're going to start at C and we're going to go to 0. So we're going to go in this direction. These will count as negative, this will count as positive, or in other words, look straight above here, we're going to end up with negative 22. Integrating in the negative direction from right to left, above counts as negative, below counts as positive. What about from B to A? Positive 5. C to B. C to B. Negative 11. A to C. A all the way to C. We're going in a positive direction. Counts as negative, counts as positive. Oh, I'm sorry. You're right. You're right. From C to A. From C to A. So we're going in the negative direction. Thank you very much. Going in the negative direction. Counts as negative, counts as positive, so the answer is negative 6. Okay, now take a look at this problem right here. Take a look at problem I. What would the absolute value effectively do to the function? Okay, so it's going to take this piece and it's going to swing it up here. That means it's going to be above the x-axis. And we are integrating from 0 to C in the positive direction. That means everything gets to count as positive. So when we put all these together, 32.
What if it was C to 0?
So if we did from C to 0, absolute value f of x dx, start at C, go to 0. Everything would, effectively it changed all the function values so they're positive. So anything above counts as positive. So the answer would be, notice we just changed the order here. So this is going to be negative 32. We'll still work there. And then from A to C, just from here to here. Did we already do this one?
No.
Nope.
That's what I thought when I.
Yeah, just from A to C. From A to C, so that's going to be integrating in a positive direction, counts as negative, counts as positive, so that's going to be positive 6. It's the exact opposite of what we had above. Okay, any questions there? Okay, so these properties that we're going to go over next are only true if we're going from left to right. In other words, if we're integrating in a positive direction. And I think these are best understood if you think of the rectangles that would be represented here. If f of x is greater than 0, for all of the function or all of the x's in that interval, then the answer, the definite integral, the signed area has got to be greater than or equal to 0. So we've got a picture that looks something like this. Here's our a, here's our b. We've got this function f that does something like this. If f is always positive, then that area is going to be positive because every single one of the function heights is positive. We're integrating in a positive direction. We've got to have a positive answer. Okay. It does leave open the possibility that it could actually equal 0. So I suppose if it were a horizontal line there, the answer could be 0. But that's the idea there. Okay. The next part says if f of x is greater than or equal to g of x for all the x's on that interval, then the definite integral, or the signed area that accumulates for f, is going to be greater than or equal to the signed area for g. So if I put that on this picture, this would be what g looks like. Is there any doubt that the signed area for g would be less than the signed area for f? That's all it asks for. Okay? And then this last one is kind of interesting. It's good for approximating, just getting a good ballpark answer. It says if little m is less than or equal to f, and that's less than or equal to big M. So a small m here and a big M here. Think of this like a minimum and a maximum. Then that means we can kind of sandwich the definite integral, the actual answer for the signed area, in between the minimum times the width of the interval and the maximum times the width of the interval. So if you think about a function like this, 1 plus the sine of x. So 1 plus the sine of x on that interval would look like this. Here's our center line right there. Okay, this is 1. It goes all the way up to 2. So I'm going to change colors here. The minimum value on this is right here. If I take that smallest value right here and I multiply it by the width of the interval, remember, you can find the width of the interval by doing b minus a. I could do the minimum is 1, b is pi, a is 0, less than or equal to the integral from 0 to pi, 1 plus sine x dx. The actual area for this has to be bigger than this little rectangle that I've drawn, doesn't it? Because all of these pieces are either above or on this little horizontal line that I represented for the top of the rectangle. Okay? The maximum for this occurs right here. The maximum for this function is 2. So if I take 2 and multiply it by this interval, b minus a, so that would be pi minus 0, that means this is pi, and that means this is 2 pi. That means the actual answer's got to be somewhere between pi and 2 pi. Because this rectangle, this green rectangle, completely encases it, and this black rectangle, every one of these function heights are above there. So it's got to be bigger than this one and less than this one. And it leaves open the possibility that it could be equal if all along it was equal to that function. The max and min were the same all the way along. Does that work? Okay. A very simple geometric idea, right? Okay. And we'll actually be able to find what that exact answer is in just a couple of days. So let's take a look at these. How do the following compare? Integral from -3 to 6 sine x dx and -3 to 6 sine theta d theta. Dummy variables, so they are exactly the same. Remember, it's the interval and the function that make the shape that determine the answer for the definite integral. Let's take a look at this right here. Integral from 0 to 10 e to the x 5x squared dx and integral from 10 to 0, e to the u plus 5u squared du. Opposites. We don't have to know what they are right now, but we can use properties of integrals to figure out how they relate to each other. Okay? So here's the next thing we're going to do, and this is where it starts to get kind of interesting. I'm going to do this problem right here. I would like you to copy this down because I think this is something that is well within the grasp of everybody here to understand and be able to reproduce. The next one on the next page, you don't have to, but it should be pretty amazing that we're going to get the same answer. So here's what we're going to do. We're going to find the answer to this in general. So if you're integrating or adding up the signed area on the identity function, okay, for any a and b, and for this I'm going to restrict it so a and b are greater than 0. So here's the function, here's a, and here's b. And I want to find out what is this area right here. I want to come up with a formula so that I could just plug it in and not have to do that long process and know exactly what it is here. So this area can be found by thinking of this as a trapezoid. How tall is this little base right here? If the function is x and I plug in an a, I get an a, right? How tall is this one? This one is a b. How far is it from here to here? B minus a. We're pretty good at that, right? So the formula for the area, we're going to use a trapezoid as 1/2 of b1 plus b2. Now, just for order's sake, I'm going to do this. I'm going to do b plus a. I'm just going to add the two bases together. And then the width is going to be b minus a. Everybody okay with that?
Wouldn't it be f of b plus f of a for the heights?
Yeah, but because the function is just x, we just already know
Oh,
it's b.
The function's just x, so plug in a b, you get a b, plug in an a, you get an a. You have to add the two, so this is 1/2 b1 plus b2, and this is the height or the width.
Yeah.
Got it? Everybody with me? Okay, so watch. If I multiply the two of these together, these have that nice property. They're called a difference of squares. So this is going to be 1/2 of b squared minus a squared. And I'm going to write it like this. I'm going to write it as b squared over 2 minus a squared over 2. So here's a formula. B squared over 2 minus a squared over 2. Now, we actually did this problem up above. We did one where the function was the identity function and the interval was from 1 to 5. From 1 to 5. This formula says, since that's a and that's b, we should get, well, let's see, it should be b squared, so that would be 5 squared over 2, minus a squared, which is 1 squared over 2. So that's going to be 25 halves minus 1/2. That's going to be 24 halves, which is 12. Isn't that what we got? Hold on one second. Slide this up here. Gosh, I hope that's right. Whew. Good thing. Got it right. Okay, Juan has a question.
So, Zach and I had looked at that problem and we just did the large triangle and then subtracted the little tiny corner. And we also ended up with 25 halves minus 1/2.
Okay. So what they did is they did this entire triangle right here, and then they subtracted this little guy right here.
Yeah.
Yep, totally fine.
So is that pretty much what this is doing? Or?
In a different way, but yes, you ended up at this result though, right? Or you could manipulate it to make it look like that, right? Okay. I think this is a little more straightforward way to do it. Okay, yours works just fine, and you'll get the same result. It's just a little more straightforward to do it as a trapezoid rather than big triangle minus little triangular sliver there. Good?
Would that work if it was like x plus 2 or something?
Well, you can just separate it.
Then you can break it apart into its pieces. Yeah, we can use that sum and difference idea. Okay, now if you want to write this down, you're welcome to. If you don't want to, you don't have to. You can just watch the video again. This is not something I would ask you to reproduce. So let's take a look at this. We're going to find a formula for this, same setup and everything, and we're going to use the definition. I think it's definition 4. We're going to use the limit. And we're going to use right endpoints because those were easy to evaluate. So the first thing we want to do is we want to figure out what delta x is. Delta x is b minus a over n. There aren't any numbers in this. That means our right end evaluation point is going to be the right end of our subinterval plus I times b minus a over n. You with me? So let's write this down. The whole idea here was that we added up a bunch of rectangles. Start at I equals 1 and go to n. And then I need a height and I need a width. Well, the function is just x. It's whatever you're going to plug in. So here are the let me make that look like an x. Here are the evaluation points right here. So a plus I times b minus a over n, those are the function heights. And I need a width. The width is always delta x. So that's going to be b minus a over n. With me there? Okay. So let's go ahead and multiply through. So this is going to be the limit as n approaches infinity. I'm going to get the sum I equals 1 to n. And when I distribute through, I get these terms. I get a times b minus a over n. Correct? And then I get plus